Malinovsky, and he's visiting us from University of Maryland at Baltimore County. His first time coming to EV, so let's welcome him.
Thank you very much for the invitation. Very nice conference. My first time here. So I'm going to talk about the hitting K primes by dice roll. So first, I will describe the history, how it's arrived to this problem. So in the beginning, in the bulletin of Institute of Mathematical Statistics was published this following problem by contributed editor from Anirban Dasgupta, and the problem was following. Suppose D1, D2, it's independent dice rolls, and Sn it's sum of dice outcomes, and dice it's fair, it's and also outcomes independent, and let denote L1 first time, discrete time, when first time sum hits set of prime numbers. So sum it's prime. So, and it was problem posted as a problem for the students, but no one saw it. And the contributing editor published the three outcomes. First outcomes, the lower bound of expectation is 2.3479. Heuristic approximation is about 7.6 of expectation. And also it was said that it's not known if the variance is finite or not. Now, it's a little bit strange in some sense because with the probability half, you stop it first time. Where for 7.6, it's a little bit unreasonable. And generally, it's easy to get lower bound since expectation in simple sum probability is L1 more equals J when J more equals 1. So, and then if you calculate few first term in this sum, it's lower bound. So it's not hard to calculate. Now, for curiosity, I did about 10 million repetition simulation Monte Carlo, and Monte Carlo shows that the average is 2.42, and also a maximum among 10 million Monte Carlo, it was 50 of L1. So it's a tail, it's not so heavy. I wrote to editor, but he said it's pretty heavy tail. It's maybe some mistake in Monte Carlo. Okay, so for some time it was lying, and then in discussion with, I forgot to say that this work is joined with Noga Alon, with Doron Zilberberg and Lucy Martinez. So, and then we solved first problem for the L1 hitting 1 prime, simple by with Noga Alon, by dividing this sum by 2 parts. Now, first part up to some level k, and another to infinity. So this part was found using a recursive algorithm, and it's really 2.4284. And second part was bounded very roughly by this constant. It's very small. Now, invariance, it's finite also. It's first, by same method, variance, it's 6.24. And also error invariance bounded by this number. It's very roughly, it's very rough bound. It's much smaller. Now only for the completeness, so a recursive algorithm simple found by this way, simple if we define PKN a probability that up to time n, up to time k, discrete time k, all sums, partial sums, they're not prime, then possible to, and by using law of total probability, simple find recursion and calculate probability of these terms using this recursion, and the upper bound of reminder, it's simple by using prime number theorem, pi n its number of primes less or equals n, using this result can be calculated simple. Now, so this is until 1 prime. Now, if we want to, the same problem when we're waiting to hit k primes, our issue became much more complicated. Now, and so LK is waiting time to hit k primes by dice, independent outcomes of fair dice. And so I wrote to Doron, and Doron did use a symbolic computation. He calculated using symbolic computation in Maple empirical outcomes up to k equals 100. And up to k equals 100, this is how behaves expectation. And the second slide is how behaves variance or standard deviation. And it's possible to see from here that generally it's something like k log k, leading term k log k. So, and variance, standard deviation is behavior of standard deviation. And he also plotted histogram. It's normalized. So it means expectation 0, variance 1, and up to k equals 100. It's some tail here, it's -4. It's not clear what is exact distribution. We did not work on distribution, but using this guess, we obtained following asymptotic results. So it's two main results here. A first result says that for any fixed positive reals epsilon delta, exists some level k0, so that for any k more than k0, a probability is that lk minus k log k more than epsilon times k log k less than delta. So it's really leading term, it's k log k. Now, the same with respect to expectation, that expectation of waiting time to hit k primes minus k log k bounded by epsilon k log k for large enough k. So for small values of k, of course, there is some other terms like k log k, but and now the issue was to prove these two results, and so I can only give to some sketch of this proof, and the proof more or less going in following way. First of all, if we denote S, so it's dice outcomes, and we're going to see it says that S hits prime if sum of outcomes. So first of all, I will describe hitting any number without any prime. So we're going to say that S hits some positive integer x if sum of outcomes exists such I that sum of outcomes d1 plus di equals this x. So we're going to deal first with the regular, hitting any number, and then we're going to switch to primes. So in first, our main results generally kind of basic, that from these results follows everyone else, says following, that exist positive C in mu, and mu between 0 and 1, such that if we denote px probabilities that sequence hits any positive integer x, this probability distance between this probability and 1 over expectation of dice outcome, that's 3.5. This is this 1 over 3.5 is 2 over 7, decay exponential with x. So it means this distance becomes smaller and smaller exponential when x grow. Now, it's from this lemma, we obtain generally kind of there's a dependence here, but from this lemma we obtain kind of similar to independent behavior for the large, so if we have x's, x1, x2, xj larger than 1, and gaps between x's satisfy certain condition for the constant C log k, and x1 pretty large, behavior of number of hits, it's similar to Bernoulli outcomes times some constant, which is e to power epsilon, where epsilon less or equals 1. So, and it's allow previous result allowed to prove this lemma, and then this lemma, what this lemma allows, to obtain, in some sense, kind of Chernow upper bound of for the tail. It means that number of hits minus, now number of hits now behaves like similar to, in some sense, to independent Bernoulli outcomes with probability of success 1 over 3.5. And number of hits has of a tail probability that it's more than A for large A. It has a Chernow bound. Now, to obtain it, it's simple to divide integers in particular way, x1, xn, divide the sequence, and then apply previous result. Now, this allow, okay, now what we can obtain here, if we denote ym as number of primes between in 1 to m his by sequence S, then if we restrict k to the values which satisfy following inequality for large A, then again pi m1, its number of primes up to m1, and k satisfy, again we obtain Chernow type bound here. And if we restrict in this way lower tail, we obtain in the same exponential decay. And then by solving, if we now restrict for large k, we restrict our pi m1, we find m1 by this restriction, we found that probability that random variable of k hits less or equal psi has exactly this decay. In the same, by the same manner, we obtain here upper tail, that is exponential decay. And then combining all together, we obtain kind of first result. Now a second result, simple obtained by all previous consideration by dividing this sum by 3 pieces. Our first piece has this order k log k, second piece has order small o 1, and third piece bounded by small o k log k. Now, possible extensions, generally the same method working if we decide talking of not six-sided, r-sided dice with arbitrary discrete probabilities, but it satisfies certain conditions. For example, it cannot be only even numbers because there is no prime going to be obtained. Or we can also talk about hitting not only set of prime numbers, for example, set of squares, anything in method going to work. Only, of course, it's not going to be 1 over 3.5. It's going to be, if it's r-sided die, it's going to be different number. Also, for curiosity, I took Doron outcomes up to 100 and fitted empirically how looks expectation. So empirical outcome, now it's overfitting because it's only can be done only for the 100. So empirical outcome, this is exactly what came. So it's also second term, which is k log k and some constants. Now, and then look on the ratio between this empirical fit and the expectation. Now it's pretty good fit, but again, it's overfit because it's only up to k equals 100. And so I think this is all.